Hello again, welcome to the second part of this lecture on the properties of composites. In the first part, we looked at how composite properties can be estimated using the rule of mixtures. Now we're going to look at some mechanisms of failure for composites building on some of these concepts. Let's start first by seeing how a composite component fails, looking at some crash testing of a woven fiber composite. So here is our subject. Still warm coming out of the autoclave, I see. Now let's drive a high-speed ram into it and see what happens. Wow, that was a bit dramatic. Looking at it in slow motion, it's very clear there's a lot going on. And it's also pretty clear that composites don't fail in compression at any singular point. They fail in a somewhat uniform manner. Here's another one. A different layup, different components, but the failure mode appears roughly the same. It fails everywhere at once. As we've just seen, the failure mode for composites is both the combination and culmination afforded by the matrix, the dispersed or reinforcing phase, and the interaction between the two. If one gets things just right, then the entire composite will fail in a brittle manner, as opposed to one select region as we've seen with other classes of materials. A modern fiber-reinforced polymeric composite component is very complicated in terms of how fibers are arranged relative to any given orientation in a layer, and then the layers themselves. The specifics of which are going outside of the scope of this course, but what we can do is look at things from a qualitative manner to describe the mechanisms by which they fail. We're going to first need to take a look at how a component the likes of which we just saw destroyed is first fabricated, and from there we can look at discrete failure modes. We need to start first with rope. Rope is, in fact, a simple machine. It is a mechanical structure that transmits power and can control movement. Here I'm depicting a wire rope, but the principles are the same for other types of rope. Bundles of wires are twisted together to form a strand, and these strands are in turn wrapped around a central core. This provides a somewhat flexible bundle of wires that can carry a great deal of load. The amount of load that can be carried by this arrangement is greater than the yield stress of the cross-section of all of the wires. This is because there is an additional amount of load that would be needed to be applied to pull each wire straight before it is actually loaded completely in tension. Compression and friction acting between each of the wires making up the rope due to their orientation act against this. Furthermore, the entire rope is not deleteriously affected if a single strand breaks. The remaining ends of the wire could still interact with the remaining unbroken wire on the same basis, preventing other wires from aligning with the orientation of a load directed along its length. Woven composites take advantage of this same type of approach. Textiles are like two-dimensional ropes. There are fibers which are woven together to form a cloth-like material, which then can be soaked in partially polymerized resin, also known as pre-impregnated or pre-preg for short, and then built up in varying orientations to form a final component. In the same way as your jumper won't fail immediately because there's a small hole in it, so too is the case for woven composites. What is potentially different is the length scale of the textile that makes up your jumper versus the length scale of, say, carbon fiber reinforced polymers, as I'm depicting on the right. The cross-sectional diameter of each fiber is around 10 microns, and these are bundled and woven together as depicted by the cross-sectional view on the bottom right. This is one pattern of many. In the same way as there are many weaves of cloth, there are 2 for fiber reinforced polymers. The arrangement of the weave may create more reinforcement in any given direction versus another, affecting final properties. So if you take this type of arrangement and drive a Formula One car into it, as you might imagine, you get a lot of potential failures all at once. Rope and cloth still hold good analogies for woven composites, Both rope and cloth are not intended to be loaded in compression, and being embedded in a matrix only helps to a small extent. Fiber-reinforced composites loaded in compression present a wide array of potential failure modes, with a few notable ones depicted here. By and large, if there is a common failure mode, it is that the matrix is overloaded at first and not able to support the fibers effectively, which in turn causes the fibers to buckle. The way in which this can manifest is according to these three mechanisms. Interlaminar failure, whereby layers of composite sheets buckle and fail between each layer, as this is where the matrix fails first. If interlaminar failure is avoided, then the next mode will be the failure of the interface between the matrix and reinforcement on a local or global basis. Finally, if the matrix also fails globally, then the fibers can kink while at the interface in some regions along their length stays intact. It is likely all three of these modes took place during the crash testing depicted earlier. While it's difficult to predict the dominant mechanism of failure in compression, generally speaking, the one that will generate the most uniform mode and overall surface area will be the one to pursue from an energy absorption perspective. Let's now see what can happen in tension. Failure of composites in tension is a bit more tractable. Let's consider a composite in an iso-strain condition loaded to failure. The composite has a matrix which is much weaker than a continuous reinforcement, which is a safe bet for most composites. The stress-strain behavior is typified by this curve, which is the superposition of the combined behavior of the matrix and reinforcement. The fibers in concert will behave as a brittle material, presenting almost no ductility. They will load elastically and then fail suddenly. This event can be observed on our composite stress-strain curve. There is a significant drop in load being carried by the composite when the fibers fail. Next, let's look at the matrix. Here I've drawn the matrix stress-strain behavior as it would not be included in the composite, that is, tested independently. The matrix behaves linearly up until a yield point and then starts to deform inelastically. The effect of this yielding of the matrix on the composite curve is demonstrated by a change in the linear response prior to the fibers fracturing. The matrix will load until it fails completely. However, there's a discrepancy in where the composite fails and where the matrix fails. Remember, the matrix behavior is being depicted outside of being included in a composite. The fact of the matter is that the behavior of both fiber and matrix are superimposed to provide the composite behavior. The complete story is that the composite loads linearly at a particular rate up to the point where the matrix yields, and this is a permanent change. Then, the rate of load carrying versus deformation decreases to the point where the fibers fracture. This leads to an instantaneous overloading of the matrix. Any resulting deformation that takes place in the composite will be the matrix, which is already yielded. This is the reason why the matrix in the composite behaves differently than that being loaded independently, presenting a lower failure stress. Regardless, the overall toughness of the composite, the area under the stress-strain curve, should be higher than that of either the matrix or fiber considered independently. Let's now look at some mechanisms affecting the fracture toughness. If we consider the same type of composite as we've just described, but instead have a crack which initiates in the matrix and starts to propagate, we'd have an arrangement that looks like this. In order for the crack to grow, it will have to break through the reinforcement. Where it breaks the reinforcement isn't always on the same plane as that where the crack is growing. When the fiber breaks off of the crack plane, this leads to a potentially large-scale deflection of the crack, as it now has to travel along the fiber interface, connect with the fiber fracture site before propagating further into the matrix and repeating. The strength of the fiber will need to be much stronger than the matrix and be long and continuous in order to realize this mechanism. To get the best return from this phenomena in terms of a higher fracture toughness, a relatively lower strength fiber with a relatively strong interfacial strength is the best route. The improvements to the overall fracture toughness is that the crack has to deflect off of a plane where the stress concentration is highest. But it also adds a whole lot new surface area to the crack flanks. This additional surface area associated with the crack can also be realized for shorter, less continuous fibers as well. With the likes of the composite depicted here, additional surface area to the crack flanks can be realized as fiber pullout. Instead of the fibers fracturing, they displace with the matrix such that they are pulled out of the regions immediate to where the crack is propagating. While the fibers can pull out of the matrix and remain unbroken while the crack is propagating, there can be regions where the fiber are bridging the crack. That is, fibers remain firmly embedded in the matrix on either side of the crack. In order for the crack to propagate, it will have to completely pull out the fiber on either side of the crack before progressing. Acting against this is a frictional bias between fiber and matrix. Note that this is not simply a continuation of the interfacial type failure previously described. In this mechanism, the fragments of broken fibers do not start acting like short fibers because the interface is either damaged or has completely failed. This mechanism relies on there being a relatively weak interface between fiber and matrix, not one that is compromised. In order to harness this mechanism specifically, one must employ short, high-strength fibers. A relatively high-strength fiber with a relatively weak interfacial strength is what makes this possible. A balance therefore needs to be struck between the fiber length, strength, and interfacial shear strength to get the right balance between strength of the overall composite and the fracture toughness. What we've seen thus far has cracks already manifested. What are some of the sources of these cracks which can propagate? As it turns out, there are loads of things that can act like a defect and therefore initiate cracks. First, let's start off with some length scale context. As I mentioned earlier, carbon fiber and carbon fiber reinforced polymers has a diameter of approximately 10 microns. These are bundled together and woven, such that each bundle is approximately a millimeter in size, as shown here. On each of the bundles, there can be some or all of these types of defects. They stem either from primary processing, that is, making the fibers themselves or weaving into a pre-preg sheet, or it can result due to improper secondary processing during the final cure of the composite. This could be poor resin quality resulting in a poor cure, cracking of the fibers, voids, and porosity. This is all at the small length scale. At the larger length scale, or the component level, then there could be issues with the final layup in terms of how the sheets are brought together. Wrinkles can form, which locally create a higher matrix to reinforcement region. There could be a foreign object that is trapped in the composite, wholesale porosity, and irregularities in the incoming woven sheets. When the composite is put into service, impact damage from foreign objects can also undermine the integrity of the overall component, often extending a great deal below the surface. These all can act as potential sites for crack initiation and progressive failure of a composite. While the mechanisms might be slightly different, there is definitely parallels with the types of defects that can occur in metallic systems. What's important to note is that the initiating defects in composite systems can appear in the reinforcement first or the matrix first, but the end result will be propagation of some type, with the two preceding examples of interfacial failure and fiber pullout being examples. So, in this part of the lecture, we looked at how woven composites are put together, and further how they can fail monolithically under compression. We further looked at how fiber-reinforced composites can fail monolithically in tension, by comparing and contrasting the relative behavior of fiber and matrix together. The tensile properties of matrix and reinforcement acting as superposition give rise to an increased toughness than either operating independently. In the presence of a flaw, two mechanisms by which fiber-reinforced polymers have their fracture toughness ameliorated on the same basis has been presented. Finally, a brief overview of the types of defects that could initiate cracking in composites was provided. That concludes this introductory lecture on the properties of composite materials. I hope that it provides a good basis for more advanced courses on the topic in coming years. Until next time.